Let's get started. Good morning, everyone. Thank you for attending today's webinar on heat pump sizing. This webinar is recorded and the recording is posted to the Code Adoption Toolkit on the Colorado Energy Office's website. If there are any issues with audio, feel free to write me in the chat. My name is Erica DeLello. I'm a senior project manager at NORESCO. This series is sponsored by the Colorado Energy Office with training materials created by NORESCO. So we've been working to provide trainings just like this one with the Colorado Energy Office over the last 5 years or so. So this is just one webinar within the series. As you can see, we've got the heat pump sizing today, and we've got one more in the heat pump series on the 26th of March on heat pump installation. And then but we are continuing our regular Wednesday webinar series as well. So if you're interested in any of these topics, I'm going to be putting the registration links in the chat. So feel free to do that and join us for that as well. We also offer tailored group trainings, role-based trainings, essentially looking at the code, the energy code, through the eyes of the person that's actually trying to comply or trying to inspect or plan review. So it's all based on your background, and we tailor the in-depth training to your experience. If you're interested in any of these types of trainings, feel free to reach out to me. I'll put my contact info in the chat as well. And yeah, it'd be great. In terms of resources, I mentioned the Code Adoption Toolkit, and that's where the recording will live, but we also have a plethora of other resources available on the Code Adoption Toolkit, including a wide variety of checklists, significant changes, documents, code comparisons, manual J&D guides, and then, as I said, all those previous recordings. One of my favorite resources is the Colorado Codes Helpline, and this is an incredible resource for anyone that lives in Colorado. You can submit a question on any of the international codes or stretch codes within Colorado, and receive a response back in just a couple days from a subject matter expert. So, for example, if you're a designer that's looking to how to navigate code applicability, you can submit a question and we get back to you. So definitely scan that QR code as well and bookmark that link, because that is a great resource to have. So last but not least, we do want to encourage questions, so feel free to use that Q&A function. We'll have a midway point where we stop to answer some questions, and then also, if time allows, at the end, I will let Ken know. Ken Carlson is our presenter today, and he is a manager or program director at NORESCO and has a plethora of experience as it relates to heat pumps and residential design. So I'm going to go ahead and stop sharing my screen and pass it over to you, Ken.
Thanks, Erica. Can you hear me okay?
Yep.
All right, so we'll begin. We'll start by sharing the presentation. All right. Erica, you see it clearly?
Yep, looks great.
Okay. All right, welcome everybody. Good morning. We're in session 2 of this heat pump workshop. Today we'll talk about evaluating dwellings, homes, and then we'll get into a little bit of heat pump sizing. Just a little touch base. We're not going to go into great detail on, what options to choose, but we will touch base on how to size heat pumps. So our agenda. So when to install a heat pump, some of the options and types of heat pumps you might consider, depending on what we're looking at and depending on the dwelling options. We'll talk a little bit about dual fuel systems and supplemental heating required with the installation of heat pumps. We'll go through some basic manual J overview on what it is and why we do it, and then we'll touch base on using a manual S to select or help guide the selection of the equipment. So overview. This session will cover considerations, procedures, and calculation methods associated with selecting the right size and type of heat pump. The objective of this particular session gain an understanding of how to assess the appropriate heat pump type for the dwelling being served, and introduction to the sizing of heat pumps, including load calculations and equipment selections. Our previous session, we did a overview of heat pumps in general, types, variations, possibilities, and some of the different technologies that are available out there. This session, again, we're talking about dwelling evaluation, heat pump sizing. We have another one coming up in a couple weeks, where we'll talk a little bit more about heat pump installation, and then we'll get in a little bit more some of the tools required, some of the installation requirements, best practices, and things that need to be considered when actually going to install heat pump systems of different types. Quick recap from last session. We talked about how heat pump works. We talked about the different types of heat pumps: air source heat pumps, water source heat pumps, air to water heat pumps. Talked a little bit options between ducted and ductless, water side options, and we also talked about hybrid fuel systems, some of the operating costs, and some of the saving calculations and paybacks associated between different fuel options. So moving into this session, when to install a heat pump. Well, that depends, right? Depends on the dwelling. If we're talking about new construction, you've got many different options. You could put just about anything in. If you want to put two separate systems in, you can. If you want to put, pure electric, if you want to go gas, if you want to go propane, all possible options. One of the main factors is probably going to be your available fuel option. If you're in suburbia, you have access to natural gas, a furnace and an HVAC system, may be viable. But again, the heat pump is also viable as well. So you have to bring electric into a dwelling. Heat pump runs on electric, backup heat would be electric. If you do bring in gas or another fuel source, that's that much infrastructure more that you need to bring to your building and that you need to run throughout the house. So there are some added costs when you're building a new construction house with adding additional fuel options for heating. So you could also evaluate, the size of the building, the need for both heating and cooling. If you need both heating and cooling, heat pump is a viable option for that. It does provide both. You have different zoning options with heat pumps, as you do with other systems for that matter, but heat pump, there are many options and types that you can go out there. Budget constraints also play a part. We did talk about water source heat pumps, and the availability to even put a water heat pump in. There are additional costs associated with that. You do need the land, you do need to dig wells, or if you put a horizontal system in, you do need to excavate. And then there just may be the homeowners, electrification goals or greenhouse gas emission reduction, right? Maybe you're going solar, with the new construction building, you want to be on all electric so that your greenhouse gas emission or contribution is as low as possible. You could end up with the zero utility bill if you did actually put solar on the roof. You may need heat pumps just to actually get the load underneath the capacity of the solar array. So there's many different things to consider. New construction installation, you've got many different options. Just real quick, we did talk about the water source heat pumps. They are a viable option. They do give better efficiency throughout the course of the year, given the constant temperature of the ground, the relatively constant temperature of the ground. It's more costly. You have to either put a horizontal system in, as shown in this picture, or you got to dig wells to be used as your heat sink, or the source as we defined in the last presentation. So definitely an option. We don't focus too much in on this. This is definitely a good way to go, but it is a little bit more costly. It's more invasive. There could be environmental regulations. The majority of the heat pumps that we're going to see, being installed and for, most homes are probably air source heat pumps. And typically that's what we'll focus a little bit more on throughout this presentation. So we did talk about air to water heat pumps. So basically, heat pump used to generate hot water throughout the dwelling. New construction, you've got options. You can put radiant flooring in. You can have a low temperature system. You can utilize a heat pump potentially with the boiler backup if needed for capacity. It's an option. It's something to consider. Again, there's an extra added cost into running piping throughout the whole entire house. If you're an existing system You know, and you have a boiler in the house, you know, your radiator design temperature is typically on the order of 180 degrees. They do make high temperature hot water, air to water heat pumps that are out there that will provide temperatures up to 170 degrees. It's an option. You probably need to add an electric boiler on top of that. There's some considerations that need to be considered when installing these types of systems. One of them, you know, front and foremost, is just the overall cost. There are some additional added components, as shown in this photo or this depiction of what a system would look like. So, you know, you've got your heat pump outside. Inside, potentially you're adding another electric boiler that's either for backup or for increased capacity. You do need to install a buffer tank. They're typically on the order of like 50 to 80 gallons. So you need room to install this tank. You've got additional components and pumps for the different types of systems throughout the home, potentially, right? So you need a little bit of a footprint inside to actually install some of this equipment. So it's not just installing a heat pump outside, you're also installing a boiler, piping, buffer tank, all inside. So, you know, if it's going into a basement, you got plenty of room and maybe not such an issue. If you don't have a basement, you're going to need a utility room big enough to house all this and still be able to service everything. You know, there is a cost factor associated with all this as well, right? You're not just changing out one boiler now you're changing out, you know, you're installing a heat pump, you're installing a buffer tank, you're potentially installing an added electric boiler if you were to go to all electric. You need to make sure that you have the electrical capacity as well to actually satisfy everything that's being installed. So something to consider, you know, not necessarily going to be the first option for every dwelling, but yeah, the technology's out there, the options are out there. You know, again, it also depends on what your fuel options are. You know, if you're up in the mountains, you don't really have anything around as far as, you know, access to, you know, natural gas. You're either going to be running on propane, oil, or you're all electric. So in situations like that, you know, this may be an option. So we'll go into a little bit on retrofit considerations. On typical dwellings, the more common being, you know, either particularly usually forced hot air. You know, you need to look at what's already there, right? What's the existing system that's in place? Is there even an existing in place, and can it be reused? The dwelling architecture plays a role, right? Do you have an attic? Do you have a basement? Do you have a crawl space? Can you put ductwork in certain places? You know, those answers will help dictate exactly what you can even put into an existing dwelling. Another thing we need to be cognizant of is the electrical availability. So if you already have an HVAC system, you have some electrical capacity that's there. If you have an all-electric house, you probably already have electrical capacity there. If you're in a much older house that wasn't really designed to even have air conditioning, period, you know, you're talking a house maybe 60 plus years old, and you don't currently have air conditioning, you've never done an electrical upgrade, your panel may not even be big enough to even put an air conditioning in, let alone heat pump or electric resistive heat as a backup. So panel size needs to be looked at, the service needs to be evaluated, and whether or not you even have additional empty breaker slots, assuming that you have nothing in the home and you're adding in probably a 220 circuit to add, you know, to install a heat pump potentially. You need to have room in that panel to actually do that. Otherwise, you know, you would require a panel upgrade. It's an extra added cost, you know, into the installation of a heat pump that needs to be considered. And then you can, of course, the evaluation, the economic performance and operating costs, you know, of replacing such a system. If it's end of life, it makes things a little bit easier. You know, if you're midlife of a system, you still have another 10 years on your existing system. You know, the math needs to be run as to whether or not it makes sense economically, assuming that it's not just, you know, personal reasons. You know, economically, that it actually makes sense to change everything out and make a switch. So we put together some retrofit options for existing installations. For example, right? So let's say you already have a furnace and you already have air conditioning and you already have ductwork throughout the house. So, and you wanted to install a heat pump. You've got basically two quick, easy options, right? There are other options, but these would probably be the two using the existing infrastructure. You can go to a dual fuel ducted air source heat pump, reuse the duct, replace the furnace, maybe put a high efficiency furnace in there, install a heat pump just like it would be installed at your AC unit in place. You can utilize the heat pump throughout, the majority of the year, and the furnace would basically be used for low ambient conditions. If you want to get off of, get natural gas and fossil fuel altogether for whatever reason that you might have, or there may be, you can go to a ducted air source heat pump with electric duct heater, with electric duct heaters as the second stage. In this situation, you almost guarantee that you're going to need electrical resistive heat on top of the heat pump. The heat pump capacity is going to be limited, one in part by just heat pumps in general, and two also by the ductwork. So you'll need that resistive heating to increase the temperature of the discharge of the unit to satisfy the heat load of the building. You could be a furnace with limited ductwork. Let's say, for example, you have a much older furnace, potentially maybe even an oil furnace down in the basement. It's got some ductwork. It was designed for, delta T of an oil furnace, which is oftentimes higher than, a gas furnace. The ductwork is probably a little bit smaller. It's not going to carry the air required, by most modern day HVAC systems, heat pumps included. So, potentially you could do dual fuel. You likely would need some new ductwork. You can do an air source heat pump with electric duct heaters. Again, probably still need new ductwork, or you just abandon the system in place, or remove it, however you want to handle that, and potentially install ductless air source heat pumps, mini splits, right, throughout your dwelling, depending on the size and how many you need. It's a viable option. Another scenario would be that you currently have no HVAC infrastructure. You've got nothing but electric baseboard. You can go two options. You can go the ductless mini split system and put heads in each individual room, or you can do a ducted air source heat pump. Now that would be dependent on whether or not you can even run ductwork, depending on what the dwelling architecture is. Do you have an attic? Can you put something in the attic? Do you have a basement or a crawl space? In which case you could put something in one of those, run ductwork, concealed in an attic or a basement. And provide heating and cooling throughout the house. And then if you already have existing hot water baseboard, air to water heat pump boiler, air to water heat pump is an option with an auxiliary boiler. Whether that auxiliary boiler it's typically electric, potentially you could use other options. If you can go ductless mini splits, right, or you could do a ducted source air heat pump with additional ducts. A lot of times in this particular case, you're either going to make a complete switch over to an heat pump system for whatever the particular reason may be, or maybe all you have in the house is a hot water baseboard. Now you want air conditioning. You can put a heat pump system in for a minimal amount more than you would just a plain old air conditioning system. You can get some of the added benefits of that heat pump heating in milder climate. And if, once the heat load of the house exceeded the capacity of the heat pump, you could still use your hot water baseboard system, provided that it's still in good working order. So just some options to go through. This is like the first step process. What do you have? What are your options? What can you put in? And then you just start going from there and figure out exactly what you can put in the house. So, for example, let's just say you had an existing standard ranch. Very simple, not very large platform. It's got electric baseboard heat. It's got no AC. It's got no ductwork. It's all right there. Being that it's electric baseboard, the electrical capacity of the home is probably more than sufficient. Sometimes you can even just remove one of the electric resistive heating strips somewhere that's not really needed, and you can use that slot, for the heat pump if you didn't have any spare capacity in the panel. You could potentially put a ducted system in if it's got an attic. It's only a few rooms, it's minimal ductwork, probably not too costly, or potentially you can put a ductless system in. If it's a small house, it doesn't have many rooms, you might only need 3 heads to satisfy the load in the building or in the dwelling. So you could leave the electric baseboard for supplemental heat, maintaining most of the heating and conditioning by the heat pump and using that electric baseboard that's already there. It's not going to cost you anything. In the weather extremes, when the heat pump capacity does not meet the heating demand of the dwelling. Just for reference, from last time, we did talk about some of the costs for heating of electric resistive heat versus a heat pump. In a million BTUs, for a comparable comparison, the cost of electrical resistive heat with the 12-cent kilowatt hour cost is $35. For a heat pump, it's only $11.72. That's using a coefficient performance of 3. So, a heat pump is probably 3 times on average, right? 3 times more efficient than just using regular electric resistive heat. So you want to bring that electric bill down, and this is these are your options, and you're looking to do something like this is a viable option in this particular case. I'm not going to go through every single case. This is just one of them, how we might evaluate a home and what those benefits might be. So let's just say, for example, now you maybe have you already have an existing AC, you already have an existing furnace. It's the end of life of that equipment. You want to do something. Maybe you want to reduce your gas bill a little bit. Maybe your natural gas costs are going up. Maybe you're running on propane, right? Or oil for that matter. And the cost is just a little bit more than you want, or you want to try to reduce your operating costs. You could potentially utilize a heat pump in the existing configuration using a new furnace with a new heat pump in lieu of that AC unit. So you could still utilize all the existing ductwork. Could use the existing furnace if it's still in good shape, or you would replace everything as a package. Typically, more often or not, that's typically the way that you would go. Everything would be matching at that point. So, the heat pump alone is probably not large enough to satisfy the dwelling. Typically, you're going to have an air conditioning unit in a typical home, somewhere between 3 and 4 tons, maybe upwards of 5. Equivalent on BTUs, 3 ton, it's 12,000 BTUs per every ton. So you probably already have 36,000 BTUs of cooling here. If you installed a heat pump, you would get 36,000 BTUs of heat. The furnace is likely more on the order of 80,000 BTUs. That's based on the demand or the heating load requirements of the dwelling. So that the heat pump would only be able to provide that 36,000 BTUs, which would satisfy the home on a good part of the heating season. On those design extremes or the very cold days, the furnace would take over and provide the heating that is required. Again, most likely you probably already have the panel capacity if you already have an air conditioning unit there. The heat pumps don't actually require a whole lot more power than a standard AC unit. So like for like, if you've got a 20-year-old AC unit or air conditioning only unit, condenser sitting outside, a new modern heat pump is likely not going to draw anything more. You probably don't have to change any kind of infrastructure that's already there. So for a little bit extra money, you get a heat pump, you get your air conditioning, you get a new furnace, you get everything. It's a viable option. Doesn't require a whole lot of infrastructure change. It's pretty much like in kind replacement. You still got to run the math and do the numbers to make sure that everything is sized accordingly, but for the most part, it's a pretty direct replacement. It does reduces your fossil fuel consumption. It'll still allow for heating, ample heating on design days. It does still get you your air conditioning, but it will reduce your heating costs, potentially reduce your heating costs, throughout the winter. The other benefit, and I mentioned this in the last session, is furnaces typically are single stage. They are designed for your heating design day, right? Colorado, Denver area, it's like 5 degrees. This furnace is essentially oversized for the majority of the heating season. You don't need 80,000 BTUs, for example, right? When it's 40 degrees outside. That's where the heat pump would actually be running, right? That's where you would get your heat from. It's a softer heat. It's a lower delta T. It could actually make your house more comfortable throughout the course of the heating season. So it's an option. Your other option, if you had a situation like this, would be to go pure heat pump, pure electric. You want to, for whatever reasons, maybe you want to reduce your greenhouse gas. Maybe you already have an air handling unit and a heat pump there with electric resistive heating. You would utilize your heat pump air handling unit. You would have to put in, or you would likely need electric resistive heating. Because again, like we said before, the heat pump capacity of the dwelling's probably not large enough. You'll need additional heat. You can use your existing ductwork. Typically, it needs to be evaluated, but oftentimes you can use your existing ductwork. You do need to evaluate your electrical capacity in the house to make sure that you have enough to satisfy or to meet the demand of the electric resistive heating that you would likely need in the air handling unit. Chances are you already have some kind of AC system there. You already have a heat pump service, electrical service outside. So you wouldn't really necessarily need to worry about that. But the electric resistive heating does draw quite a demand. It's typically a higher capacity because it is resistive heat. You do need to evaluate the electrical service and whether or not you have enough room in the panel to actually run a new circuit for this. Again, just back to what we evaluated for costs, apples to apples, per million BTUs, cost for propane per million BTUs, cost of a heat pump per million BTUs, cost of natural gas for BTUs. This is based on $1 a therm, electric cost of 12 cents a kilowatt hour, and a propane cost of $2.18 per gallon. Propane is definitely more expensive. Heat pump and natural gas, they're comparable in pricing, but things will fluctuate. Me personally, my natural gas costs have probably gone up 50% in the past 5 years. 5 years ago, when I moved in the house I'm at now, I was paying $1.10 a therm. I'm up to $1.60 a therm. So heat pumps, even for me personally, a heat pump is actually starting to look a little bit more enticing. My electric costs, although they are increasing, have not gone up at the same rate as the natural gas has. So it's an option for certain people, for certain areas, and depending on what your options are. One thing I'm not going to go into a great amount of detail on this, but I did want to touch base on line set routing. We'll go a little bit more into this probably during the installation, but something to be considered when you're evaluating a home, right? And this goes for the installation of, if it's a home that doesn't already have air conditioning systems or anything like that, or even if it does, oftentimes you're changing out the line set, or maybe you're relocating equipment. How you're getting the line set, the refrigerant piping from the outdoor unit to the indoor unit, it has to be evaluated. This is just a couple of photos of some mini splits that have been installed, but like the photo on the right, this appears to be a multi-zone. You've got a head over here in the front of the house. You got a head up on the second story. You might even have the head up somewhere over the front of the house. This particular case, they ran up and around and put it in line set hideaway. It hides things. You can paint it. It makes it much for a clean installation. If you don't have an attic, you're not putting ductwork in, or maybe it's just a quicker installation to put mini splits in. You'll have to consider how you're gonna run your line set. And this even applies for a standard split system if you're gonna put an air handling unit in the attic. Like, you need to get lines, refrigeration piping from the outdoor unit to the indoor unit in an existing home. Unless you're gonna rip out the walls, which most people and contractors don't want to do unless the homeowner's gonna ask for it. It's gonna be an added cost. You're gonna go up the side of a house, right? Or you're gonna go through, from one side of a house into the house, through a basement or crawl space, and then to the other side of the house. But that does need to be evaluated, how you're getting your refrigerant piping from point A to point B. In the case where you're putting a mini splits or multi-head mini splits, right? You might have one outdoor unit and 3 heads. You need to evaluate how you're going to get those line sets to all those locations. And that also leads into where you're actually going to put some of those indoor units based on how you're going to get your refrigeration piping from point A to point B. I don't want to talk too much about this. It's more for like the installing contractor to be concerned with, but it is something that needs to be evaluated when you're looking at options for installing a heat pump system into an existing dwelling. So we're going to go into heat pump sizing and manual J's in a moment. Does anybody have any questions up until this point on what we just kind of talked about?
We do have some questions and some comments. First question is, what price range should someone expect for an air to water system if boiler, piping, radiators, baseboards are already in place?
It's going to vary a little bit. It's going to be more than a direct replacement. It depends on if you've got an increased panel size that would actually add to the cost. If I take a guess at it, you're probably on the order, you're over 10,000, probably between 10 and 15 for a system such as that. By the time you get done with the heat pump, the extra added piping and everything like that, you're somewhere in the order of 10 to 15,000 ballpark.
Yeah, it's obviously an estimate, and it depends on where you live
It
too.
depends on where you live. It depends on what you have. It depends on the infrastructure you have, where everything is going. But 10 being on the very low side is probably unlikely. 15 is probably much closer to what you'd be paying. And you could probably say plus or minus 5 from that 15 mark.
Okay, next question. I guess comment with some folks in the chat are commenting on how if you, in many cases in Colorado, if you install a cold climate air source heat pump, a lot of the times you might not need electric resistance heat. So just something to note there.
It's possible. So a lot of times, and just I want to add a comment on that. A lot of times, the heat pump will carry you probably further than you think. So a lot of times when you do these manual J's, they take into a lot of different factors to make sure that the equipment is sized properly, but it's not oversized dramatically where it's going to affect the performance too much. So if you do the evaluation that says that you need, heat pump plus electric resistive heating to meet the requirements of down to 5 degrees, and the heat pump's going to bring you to 30, just for example, these are just random numbers. A lot of times that heat pump might bring you further than you think. And just to make like a point here. So I actually just happened to be on LinkedIn like a month ago when we had those cold spells. It happened to be actually a woman at work, and I know who she is. I've done some gone back and forth with emails, but I didn't realize she lived in North Carolina. North Carolina was like 20 degrees or 25 degrees, and I didn't know she had a dual fuel system. So she actually posted something, said, dual fuel system, it's 25 degrees out. My dual fuel system furnace still hasn't kicked on. I'm still running on a heat pump. So even at 25 degrees, being that he's, anticipated probably needed that furnace at, their design, I can't imagine it's much more than 20 degrees on the out at an ambient. She's still running on a heat pump, maintaining the building dwelling, even down into the 20 degrees with just a heat pump. So, it varies, it depends. But a lot of times the heat pump, you don't need the electric resistive heating. But we'll talk a little bit about that coming up when we do these manual J's. We'll run through a scenario of what you're actually doing in a manual J.
Perfect, thanks. And that actually dovetails into the next question. For supplemental electric heat, does the heat pump run at the same time as electric resistance heat?
Yes. Yeah. And it does for an electric resistant heat, yes, because the heat pump is first and the electric resistive heat is downstream of the heat pump. When you go to those dual fuel systems, that's a complete different switchover, because oftentimes the heat pump sits on top of the furnace. The furnace would actually end up heating the refrigerant, right? So in cases like that, it's a hard switchover. So the heat pump down to a certain ambient condition that you would choose, and then below that, you would shut off the heat pump, and then you would go, the furnace would take over.
Perfect, thanks, Ken. Can you speak to the risk of contractors recommending oversized units in order to make a larger sale?
Can I speak to that? Yes. I will tell you that oftentimes it's probably not to make necessarily extra money on that. Oftentimes it's either contractors using rule of thumbs, replacing exactly what was there, right? That causes a lot of oversizing. A lot of times, to make more money on a larger piece of equipment, there might be some small instances there, but I think most of the oversizing that's done in the industry, it's either because it's been replaced like in kind, and nobody did a manual J to figure out exactly what was required, or they're using old school rule of thumbs. And don't get me wrong, I've done this for back of the napkin, math. In my past is, 40 BTUs per square foot gets you the heating that you need for the dwelling. It gets you probably close, but that's a very old number based on contractors from 60 years ago when it was 2x4 construction, loose housing, poor insulation. That rule of thumb doesn't apply anymore, particularly if you're in a newer home that's not 65 years old. So you can really end up oversizing equipment, by using those old rule of thumbs, or just replacing exactly what's there. Particularly if that unit was installed 40 years ago.
Definitely, that makes a lot of sense. Okay, one more for you. If someone opts for a dual fuel, does that make it easier or harder or the same to go in later and switch to a fully electric heat pump?
It makes it That's twofold. So it's pretty much, it would basically make it the same to later switch to a fully electric heat pump with electric resistive heating. So however, you can't, it's unlikely that you're going to put a dual fuel system with a heat pump and decide 5 years from now that you're going to go all electric, and that heat pump is still going to maintain. Like, you're still going to be able to use that heat pump. There's a good chance that you would be just starting over, completely. So I mean, if you have an idea like 5 years from now that you want to put a heat pump and go all electric, you might want to consider doing that sooner than later. Otherwise, you're just going to be replacing an entire system just to replace an entire system again. But the infrastructure that's there would remain. So your ductwork would remain. So, the effort changing over now, it would be the same effort changing over 5 or 10 years from now.
Makes sense. Okay, one more question and then we'll keep going. In the slide number 9 example, how did you account for heat pump operating costs during cold weather run hours as heating capacity decreases with lower ambient temperatures?
Okay, so the heat pump cost, we use a COP of 3. I didn't run an evaluation to get a COP during throughout all the bin hours plus the resistive heat. The COP on most heat pumps goes down to about 2 when you get to low ambient conditions, and then you would need your electric resistive heating on top of that, creating even a lower COP. The COP of a heat pump typically is above 3, above like 30 degrees or so. Therefore, being actually higher and more efficient and actually costing less than that posted value. So that value is really just an average COP. It's not necessarily accounting for every bin data throughout the range, if that makes sense. So it's just a blended estimate. It's not accounting for all the low ambient resistive heat that you might necessarily need. But it's not overstating the COP either, just for clarity. The COP is typically 3.5, 3.7, 3.8 above 30 degrees. It's around 3, around 32 degrees. And then it goes around to like 2, oftentimes 1.8, 1.9, 2. When you start getting those low ambient conditions of like 17, 10, 5 degrees.
Thanks, Ken. Yeah, more of an average, it sounds like.
It's more of an average, yeah.
Okay, well, thanks everyone for your questions. We're going to keep on chugging along here. So I'll pass it back to you, Ken.
Okay, so back to the question of oversizing, anything like that. So this is the way in which you prevent oversizing equipment, or undersizing for that matter. And that is using what they call a manual J. All right. So what a manual J does, it provides a detailed procedure for heating and cooling load calculations. It's essentially heat loss, heat gain. ACCA puts out this particular manual J manual. It gives you procedures. It gives you U values, resistive values, and U values for different material, and you put that all into their manual J spreadsheet, and it will basically spit out your heat loss on a design day. Or you can use, which most people are doing these days, is you can use a program. There's multiple different programs that are out there. There's a couple of programs out there that are even free to use. You can even toy around with. If you do some Google searches, you'll be able to find them, or you can pay for different platforms that are out there. But establishing what your actual heat load, heat gain on a house is crucial to actually properly sizing a heat pump. And it's not just even a heat pump, for any HVAC system. So what do we actually do when we do a manual J? So one, you need to know what your design criteria is, right? So since we're talking in Colorado, and I'm just going to pick Denver, it's a major city, major hub. Your ASHRAE design criteria for Denver is 5.8 degrees at the 99th percentile. So what does that actually mean? Where do we get that number from? So if anybody's interested, you can go to ASHRAE. They've got, type Google search ASHRAE design data. It'll pop up. They've got a list of all cities throughout the United States and even outside. And this is what you'll actually see. This is the criteria that you'll use to actually design your systems and what you would use in a manual J. So if we just focus in on heating for the moment, annual heating, coldest month, heating dry bulb. So your heating dry bulb, they give you two values, right? 99% and 99.6%. What this 99% means is that 99% of the time it's above 5.8 degrees. All right. So this is the value. I mean, you can design to 99.6, but typically you design to 99 percentile. You'll design for 5.8 degrees. So where did they get this information from? I'm going to show you in this next slide. This is something that we use oftentimes to evaluate HVAC systems and to calculate savings and costs and do load analysis. This has been data, right? These have been hours. So this is for Denver International Airport. These are the temperatures you have. These are the values, the number of hours at each hour interval, right, within this temperature. So in January, there were 7 hours, and I should know this is averaged over multiple years. They haven't updated this in a while, but this averages from like 1993 to 2005 or something like that, 2007. But in this particular example, if we just look at, oh, I apologize for that. If we look at Denver and we look at the 10 to 15 degree range, at between midnight and 1 o'clock, there's 7 hours in that range. Forget about the actual individual hour ranges, but it's more so important to be looking at the total so that you actually see how many hours on average you're typically in these low ambient conditions. So a lot of times when people are like, oh, it gets very, very cold here, it does get very cold there. But the amount of time spent in, anywhere around 0 degrees, you're only at 20 hours, right? So most of your heating, even in Denver, right? If you figure that you're probably in heating between 60 degrees and, roughly 25. So between 25 and 60 is most of your heating. Below that, you're only about 120 hours below 20 degrees. So even though you're designing for 5.8, most of your heating requirement is actually well above that. I just wanted to point that out to everybody because a lot of time, people oftentimes talk about, oh, it gets very, very cold here, and it does, right? But it's a small amount. So you're talking a smaller range, a smaller amount of time in which you would actually need supplemental heat, oftentimes when installing a heat pump. So we're going to talk about two different things. We're going to talk about manual J calculation. It's a method for calculating the heat loss and the heat gain of a dwelling. And we'll talk a little bit about manual S procedures. I'm really not going to go into a great deal about this, but through ACCA, they have what's called a manual S. It's for selecting the size of equipment based on your manual J. So we'll go into a little bit of that criteria. These are manuals for purchase. You can buy them right off of ACCA's website. They're not a ridiculous amount of money. And there's a lot of good information in there. And it's a lot. So if anybody picks up a manual S or even a manual J book and you start reading through it, there's a lot of stuff in there. It's overwhelming at first, but if you start to read it and you kind of go through it, it'll start making a little bit more sense. And then there's also what they have is a manual D, and this goes into sizing of ductwork to ensure that you've got adequately sized ductwork for the amount of airflow and your temperature differentials for that matter, available for the system to make sure that you're not restricted, to make sure that you have enough airflow, or you make sure that you have properly sized ductwork for the airflow. We're just really going to talk about mentioning this. I could spend a whole day just talking about how to actually use a manual D and how to go through it. So I want everybody just be know that these are out there to actually properly size HVAC systems in their totality. So moving into manual J. So what it actually does, and how you actually calculate a manual J. Now, be very mindful that this is a very simplified, basic like manual J. It's really just to state the principle behind this and what we're actually doing in a manual J and why you actually need to do such a calculation. So first and foremost, heat loss, right? Heat loss is calculated with this formula down at the bottom. BTUs equals the U value, which is the coefficient of thermal transmittance. It is the opposite of an R value, right? Which is the coefficient of thermal resistance. Everybody's probably seen insulation's got an R value, R10, 20, 30, right? 1 over R is your U value. So better resistive, the higher the R value, the less transmittant the less that material transfers energy, all right, because of this inverse relationship. You get your U value, you multiply your square footage, your area, and your delta T. In this particular case, it's Denver, it's 5.8 degree design criteria. Or inside, we want to maintain at 70 degrees, your delta T 64.2. Our dwelling that we're going to do an analysis on, it's 1,000 square feet. It's got 9-foot ceilings. It's well insulated. It's got 2 exterior doors and 6 double pane windows. All right. And then our indoor and outdoor design criteria is at 70 and 5.8 degrees. So what do we do? So we run a heat loss calculation using that formula for everything that's within the house, right? So we've got our walls, we've got our area, we count using that formula, right? And a U value, that, and by the way, this U value is can be found in that book. It's a combination of each R value of the material, your outer layer, your inner layer of insulation. If we're talking about a wall, you got your outer layer sheathing, you got your inner insulation, and then you've got your interior sheetrock. All of those R values need to be added up, inverse, and to get your U value. So this U value is actually a total of all the material in the wall. Regardless of that, we calculate that you've got 3,873 BTU loss at 5.8 degrees through the walls. You've got your 6 windows. They've got a U value of 0.3. This can also be looked up depending on the type of window you have. We calculated a BTU loss of 1,733. We do our doors, we get 514 BTUs. Our ceilings at 1,000 square feet, we get about almost 1,700 BTUs. You get your floor, you get another 2,000. You add all that up, you've got 9,908 BTU total loss of your dwelling. All right. So now we've got our total loss on the design day. So what do we do with this? So we take this and we go to our manual S to help size, right, our equipment. So what does manual S say? So manual S says a lot, by the way. So basic form, manual S says the heating capacity of the selected unit must be greater than or equal to the calculated heating load. Supplemental heating required if heating capacity cannot meet the heating load. That would be like electric resistive heating or electric baseboard or whatever you might have. So then we take, so it also states, put it down here on the bottom, that, and this is for variable equipment, manual S states the minimum compressor heating size factor must be less than 0.8. The minimum compressor heating size factor basically says that your minimum heat pump output over your heat load requirement has to be less than 0.8. It's basically a turn down rating, right? So the heat pump, if it's oversized, the minimum value it puts out must be less than 80% of your heat loss. So using all this information, plus we have multiple, let's just say we're putting a mini split system in, for example. We've got 3 options. We've got a 9,000 BTU, a 12,000 BTU, or an 18,000 BTU. The 9,000 BTU is not going to be enough. It's got to be at least 9,908 BTU output. So let's say we choose a 12,000 BTU unit. We at a 12,000 BTU unit, we put an altitude correction factor of 0.92. This comes out of the manual S. Your actual capacity of that unit would be 11,040 BTUs. So still above the 9,908. The turn down rating of that unit would be, and I didn't put correction factors into this, but it turns down to 4,000 BTUs. If we use that 0.8 minimum compressor heating size factor of 0.8 on that 9,908, it has to be able to turn down less than 7,926 BTUs. So it meets this criteria, and it meets this criteria of being above the 9,908. So we would select the 12,000 BTU unit. So now what I'm gonna mention something on this, and this is important. A lot of times this is where, you know, heat pumps typically fail, is that the heat pump has to defrost. All right. So even though you've got 12,000 BTUs of capacity, right, when it's 5 degrees outside, the heat pump states that it will do 12,000 BTUs per hour, right, at full capacity, which it will. Right? Your heating output, it will give you full heating output at those lower capacities. However, it does have to defrost. So there is a bit of a D rate on this 12,000 BTU. So if you are sizing heat pumps, you definitely want to be on the higher range, but not so high that you put twice the size in there. I didn't actually put this in in the slide, but I did look up a manufacturers for 18,000 BTU. So if you go to an 18,000 BTU, let's just say you want to oversize it, you want to account for that defrost cycle. If you go to an 18,000 BTU, your minimum output on that 18,000 BTUs is actually above the minimum required of the manual S of that 0.8 times your heat loss, your 9,908. So you would actually be oversized and you wouldn't be within compliance of the manual S. So you would actually be too high. So that's where your electric resistive heating would actually come in. So, and that's where that supplemental heating comes in on heat pumps, is that you need to account for that extra, but you want to just oversize the heat pump to account for that. Right. So you wouldn't, if you need 60,000 BTUs and, the biggest heat pump you can get is, say, 48,000 BTUs. Like, you don't want to put 60,000 BTUs a heat pump. They're just going to be too oversized. Staging with electric resistive heat is the best way to do it. It might not be the most efficient, but it'll get you where you need to be without being oversized, and it'll make the dwelling much more comfortable, as opposed to being oversized and short cycling unit. And that just doesn't go for heat pumps. That also goes for any kind of furnace or anything else that you'd be putting in. Oversized equipment tends to cycle too much. Heat pumps can turn down a lot, but they do have their limitations. So that's just a basic quick analysis of what you're doing in a manual J and how you're selecting equipment. There's a lot more to this. We can go on for hours and hours talking about manual J's, the different options, manual S's, manual J's. All we did was sensible heat. You start getting into cooling, you got to start talking about sensible heat plus latent heat. And there's a lot more that goes into it. There's air infiltration options that can be chosen. This is just the basic analysis, just to kind of show, what a manual J does, right? And what you do with those numbers once you actually have them. So that's basically, that's where we're at. That's the end of this particular session. If anybody
That's
has any
great, Ken.
questions, we've got a few minutes that we can actually take some questions.
Thank you. Yeah, that was really helpful. Just breaking it down like that and putting it into an example. I know that helped me. So we do have some questions for you. You touched on this already with the altitude duration for heat pumps. Is it comparable to how gas furnaces should be derated for altitude?
Yeah, so that duration is based out of the manual S, and it has to do with air density across a coil. All right. So gas furnace can actually be derated. So that would actually just be your CFM rating. Your gas furnace can actually be derated even more than that because of the actual combustion process. And being at a higher altitude, your actual gas output could actually be lower. So you actually derate yourself twice. One, because the airflow going across the coil, and then two, the derate of the furnace. Now, one thing I should mention is that it should still apply. The derating across the furnace would be different though than that coil. Just to clarify, you should be able to find that in the manual list though.
Perfect. Thank you. Okay, how does manual J take into account heat gain due to average passive solar gain?
It'll run the math in the background. The example that we did is just real basic, straightforward. It doesn't take into heat gain. The programs and even the manual J, like if you did it the manual way in the manual J, it's an advanced Excel spreadsheet. You put in all the inputs, you would put in what the north facing wall is, and it would add a solar load to that north facing wall. If you put it into a digital program, you would orient the dwelling with to north, right? And it would account for the solar load, on that southern facing wall, or even east or west, depending. And oftentimes it'll ask you whether or not that the side is shaded or full sun. So the program itself would actually account for that. And you can do it manually if you wanted to, but it's a lot.
Right, thank you. Okay, let's see here. For those of you who are asking about the recorded videos and PowerPoints, we'll be working with the Colorado Energy Office to get it posted to the Code Adoption Toolkit. So definitely take a look at that toolkit. I linked it in the chat. Are there any drawbacks to oversizing a heat pump with anticipation for a future addition to a home?
Yeah, if you never put that addition on, you've got a severely oversized heat pump. Um, that's probably going to be the biggest drawback. You know, there are some disadvantages to it. You know, depending on what the time frame of that addition is, you know, you might want to go down a different route of just sizing for what you have for that dwelling, and then when you put the addition in, you put a supplemental unit, you know, in its place. If you did do something like a multi-zone split systems, just so that everybody's aware, is typically a multi-zone, depending on the size, has multiple ports. So multi-zone at 24,000 BTUs has like 2 or 3 ports. When you get up to like 48,000 BTUs, I think it's got up to 5 or 6 ports. So that basically means 5 or 6 heads that you can attach to that unit, but you don't have to. So if you just needed 3 or 2 for your existing dwelling, and then you're going to put an addition on later on, you can actually oversize the unit, only utilize 2 ports, and then you can add a head, right? Or you can add an air handler, you know, at a later time. But that would only be in that particular case where you actually utilize the multi-zone heat pump. Otherwise, I would tell you just stick to the actual basic dwelling and then just add an additional unit for the addition. Unless the addition's small, in which case you can if it's oversized just a little bit, you could do it. But if you're talking about oversizing like 50% because of a future, I don't know. I wouldn't necessarily recommend that.
Thanks, Ken. Okay, is it better to size the heat pump for cooling so it's not oversized and use supplemental heat during heating when needed?
Yep. Yeah, so I didn't really get into that. So there's a whole procedure in the manual as that when you're using like say a variable heat pump, for example, there's cooling limitations to that as well. So depending on where you're at, what your zoning is, and how much heating you have, oftentimes, right, if you're in a somewhat mild climate, you would actually size the heat pump for the cooling load, and then you would use supplemental heating for your additional heating load. You know, if you're in a dry climate, you really don't have a cooling load. I've asked this question actually out in Colorado as to what the code requirements are, you know, for sizing. And, you know, where I asked, they're like, there is no code requirement for sizing it. So you could actually, you could in that particular case, oversize and size it just for heating, but you will have a very large, you know, heat pump, instead of, you know, probably a little bit more for you basically end up with an oversized. But to answer that question, typically you would size for cooling and then you would add in supplemental heating for the additional heating requirements.
Gotcha. So that kind of answers the next question a little bit. I've been taught by Excel to size the heat pump if it is an inverter-driven variable speed heat pump per the heating load, which is oversizing in a lot of instances the cooling load. So do we oversize cooling? Is that correct?
No, it's I think that actually depends on where you're at. If you're on a climate that's driven by heating, you'll size it to the heating load. Right. If you're in a multi-mix climate, you'll size it for the lesser of the two to prevent the equipment from being oversized. For example, right? I personally am not in Colorado. I'm actually in New Jersey. So out here, we actually size equipment. If I was to put a heat pump in, I would size it for the cooling load, and I'd have to add supplemental heating for the heat pump. Depending on where you're at over here, there is actually an engineering analysis that's done when you go to submit a permit. They will actually look for that and they'll flag it if you try to oversize something too much. You know, like I said before, like if you get into a climate that's really driven by heat, you know, and it's very dry like it is in Colorado. I actually ran some numbers on that. I didn't want to show it because it starts to add confusion. It brings us to this conversation. Is that if you actually did that manual J for the cooling load, you know, in Denver, you end up with a very small number. It ends up being like 3,000 BTUs or something like that. The turn down ratio on the heat pump actually can't even turn down that far. So per the manual S, you're actually oversized. So I didn't want to do that because it becomes a poor example, right? So, and that's basically the question that you're asking is what do you do in a situation where your cooling load is so low? I'd probably go to local jurisdiction to see if there's any requirements on that, but I would likely size it more so for the heating capacity and negate the cooling load because you probably barely use the cooling feature out of it.
Yeah, that's a good point, Ken. You know, since we are a home rule state, it's really important to check with your jurisdiction on their specific code requirements. We work with a lot of different jurisdictions that amend these things. So if you do have questions, I posted the link in the chat for the helpline, and we can help answer those specific to each jurisdiction that you're working in. We are at time, but I'm going to stop the recording, but we do have a couple more questions if you've got time, Ken.
Yeah, absolutely.
Okay, great. And so once you do exit out of this webinar, a post-training survey will pop up. If you could please take a minute to fill that out, just takes like literally 60 seconds. That would be great and a big help to us. Okay.